by 2, where does it end up? At 2i. Okay, and let's multiply this out and make sure that we agree with that. So I just FOILed there. So if I multiply that, I get 1 plus I plus I plus I squared. What's I squared?
1.
That's 1.
It is. This 1s is the 2i that I was expecting. One of the reasons I like this section is we can go back to chapter 2 stuff. Do you remember that we did rotations and scalings as matrices way back? So how do I rotate by theta? What does the matrix look like? What's the first column? Cosine theta. Sine theta.
Negative sign.
Minus sine theta. In scaling, how do I factor C? S? Call it S. Now call it, yeah, those are what are the two worst letters? I'm going to say A. How do I scale by A?
A 0, 0, A.
Okay, and then I can put these together and make a rotating scaling matrix. So if I multiply these, can you see the order doesn't matter? I can scale and rotate or rotate and scale and end up in the same place. So this is so the general form of a rotating scaling matrix looks like this. Say it again? Oh, it's rotating and so what I want to do is I want a matrix that rotates and scales at the same time. So the general shape of a rotating scaling matrix, one that does both at the same time, looks like this. So we don't have to worry about that. We don't need the determinant to be 1. It's down to. So let's look at this 1 plus I. Multiplying by 1 plus I is rotates by 45 degrees and scales by the square root of 2. We can actually do this as a matrix. The angle is 45 degrees, and A is the square root of 2. So we put it together. What's cosine of 45 degrees? 1 over square root of 2, square root of 2, 1 over square root of 2, minus square root of 2 times 10 over square root of 2. and then square root of 2. So the matrix that represents rotating by 45 degrees and scaling by square root of 2 is that matrix. Going back to our example. So we can think of this complex number. We multiply that, it does a rotation and a scaling. Let's work this out. So what this is going to do is I think about 1 as a vector and multiply by 4 plus 3i. So a couple things. So I'll do it this way, first of all, and then I'll show you a shortcut, because it should remind you of something else. Is what's the length of this vector? 5. And I worked it out, that's 53 degrees. Rotate by 53 degrees. Scale by 5. Yeah, we're so close to essentially the column at a time approach. What's this length? What's it? Yeah, the angle's 53, right? So this is.
Not 37, it's a 50.
Oh, is it 37? Is it 37? Oh, hold on.
Because
Over
the little
4.
angle.
Oh,
to
yeah, you're
the-
right, you're right. I agree with you. 37, that's what I was thinking. Did you know that?
I don't know, I just know the little angle to the little.
Oh, got it, okay, yeah.
Yeah.
I agree. 37, very good. So this distance is 5 times the cosine of 37. And then this one is 5 times the sine of 37. I just want to focus on the first column here. So to get the first column of that matrix, it's a rotation scaling matrix, where there's the angle, and there's the scaling factor. But what is 5 times cosine 37 degrees? What's this distance? 4. And in the vertical direction, 5 times sine 37 degrees. So do you see how the first column of the rotation scaling matrix can exactly be read off from the eigenvalue? And then, if it's rotation scaling, the first column is AB, the second column is negative B, A. So what do I do for the second column? So this is going to be our R matrix. So again, big picture, is we're trying to break our A down as something. So one of the pieces of the puzzle is we're trying to, since A started with only real numbers, is we want to come up with a basis so the middle matrix is nice. And it turns out the nice matrix is a rotation scaling matrix. And you can easily get that rotation scaling matrix just from the one complex eigenvalue. Got that? Essentially, there's a lot of steps in there, but what's going to happen is you're going to want to break this down as an SR S inverse. And for the R matrix, all you need to do is look at this 4 plus 3i and drop that into the first column.
And so R is always scalar rotation.